Hello, everyone. We are TNT, which stands for Translational Neuroengineering Technologies, and we are an interdisciplinary student group that is looking to bridge the neuroengineering community at Hopkins. We organize academic events like this Journal Club series, as well as our seminar series, as well as professional development events and social events as well. So make sure to check out our website and join our mailing list if you want to learn more about us or get involved. If you have questions during this session, feel free to unmute yourselves or type in the chat. And there will be a call that will be sent out towards the end of the session, just asking questions so that we can plan future events better. So please make sure to fill that out. And I would just like to introduce our speaker, Dr. Charley Della Santina, who's also my advisor. And Charley is a professor, researcher, and clinician in the Department of Otolaryngology, head and neck surgery here at Hopkins. His lab research focuses on restoring functionality of the inner ear, and our main application is the translational development of the vestibular implant. Today, Charley will be covering the foundational work of David Robinson, who was a founding member of Hopkins Department of Biomedical Engineering, and the focus will be on the use of control systems to model the mechanics of eye movements, specifically the vestibulo-ocular reflex. So without further ado, welcome Charley, and take it off.
All right, thanks very much. I'm gonna go ahead and just share my screen. 1 second, please. Take it off is usually what you shout out when you want people to disrobe, but I don't think that's what she meant.
Yeah, sorry about that.
All right, good. Can you see my screen? Can somebody give me a thumbs up if you can see? Oh, it's not sharing. Or is it sharing?
Yep, we can see your slide.
Yeah, you see using linear systems, right?
Yep.
Okay, all right, because it's not highlighting normally. All right, great. Well, thanks everyone. Can I just, it's helpful for me to get a quick sense of the people who are on this call. I know some might watch this virtually in the future. How many actually read the paper that was sent out? Can I see a quick show of hands? Okay, and how many of the people here have never encountered Laplace transforms in previous courses? Okay, and how many have never heard of the vestibular system? Okay, good enough. All right, so I want to try to tune this to the interests and needs of everybody here. We have a diverse group, and people who are interested in the work that TNT promotes can come at it from engineering, can come at it from neuroscience, and I want to be inclusive for everybody. So if you have any question at any point, please chime in. Just unmute yourself and speak, because that way I don't have to be constantly looking for the raised hand symbol. But if one of our moderators could take a look and keep an eye out for any kind of chat questions that come in, please just interrupt me and let me know at your discretion. The other thing is that I get it. If you're an engineer who's done all kinds of engineering stuff and the physiology is brand new to you, it's okay if you don't completely follow it. It's enough that you just sort of hear about it and you can go back and read up more on it in the future if you'd like. And conversely, if you just haven't had much exposure to linear systems theory, or what Dr. Robinson's paper calls control systems theory, it's okay. I mostly just want you to be aware that there is a way of modeling systems that could be useful to you. And it really isn't that hard to learn, even if you're brand new to it today. So the key paper, by the way, you can see my mouse, correct? Great. The key paper we're going to focus on today is one of the classics. And Thalia, when she described this TNT series to me, said what we really want to do is choose several of the classic papers, foundational papers for neuroengineering. And I would count this as one of them, along with, Hodgkin and Huxley would be another. And I think everybody involved in neuroengineering of some sort should have heard about this and at least get the concepts. And so nothing I talk about here today is my own work at all. I'm really going to work from material that was written and actually presented to me directly by Dr. Robinson, who was one of the founders of biomedical engineering, not only here at Johns Hopkins, but I would argue globally. I think that Robinson's work bringing electrical engineering techniques to the study of physiology, in this case of eye movements, could be seen as one of the initial events in the creation of biomedical engineering as a field of study. And the paper in particular we're talking about is this classic Annual Reviews of Neuroscience 1981 paper on the use of control systems analysis in the neurophysiology of eye movements. And I'd like to point out to you that even if your work has nothing to do with eye movements, and if you're not particularly interested in it, stay with me, because in this case, although eye movements themselves are interesting, this is really just a case study in how to model a physiologic system, and probably you're interested in that. Robinson himself kind of narrowed it down into a few quick lines. He said, making a mathematical model makes you think. And that exercise is just too easily bypassed by people who mostly just collect facts, collect empiric data, for instance. But another way of looking at this is that, modeling alone without those empiric data ends up being just an exercise in making hypotheses that you never test. And so I hope all of you will marry these ideas of modeling, hypothesis generation, getting empiric data to test your hypotheses. Here Robinson said the oculomotor system is kind of a cartoon of motor control throughout the rest of the body, in the sense that a cartoon extracts the essence of a picture in just a few lines without unnecessary detail. And I'm going to follow his theme. For those of you who read the whole paper, you can see that it gets into great detail about many different eye movement systems, optokinetic response and saccades. We're going to focus only on one of them today, the vestibulo-ocular reflex, which is amenable to this type of modeling. And Robinson said that systems analysis not only organizes current knowledge, but it leads to predictions by way of hypotheses known as models. And I think you'll see a really nice example of that today. So how do you use linear systems theory to model some real system, which for everybody here on this call is going to be probably some physiologic system, but it doesn't have to be. You can be modeling the dynamics of a car or a jet airplane, or the pharmacokinetics or pharmacodynamics of a drug as it's being processed through a system. It doesn't have to be muscles moving things, for instance, which is what we'll talk about today. But you'd start with the basics. You'd say, well, I'm going to define what the system does, or I'm going to learn about its anatomy and physiology. And then I'm going to systematically break it apart and think, well, what are all the inputs? What are all the outputs that I can measure? What are the intermediate signals that I can intercept and listen to, or maybe even inject into the system? And what are the subsystems between those points? You just draw it down on paper as a signal flow diagram. And then, since we're going to talk about modeling things that happen in time, this is really time domain signals. And I'm going to try to convince you that it's just way easier most of the time to take time domain functions and convert them into the Laplace domain. And if that's unfamiliar to you, don't worry, we're going to talk about it. Once you're in the Laplace domain of modeling time signals, then you either measure, or sometimes you just guess, or sometimes you can derive from first principles of basic physics a transfer function for each block, each subsystem, which tells you how it takes its input and turns it into its output. And then you can combine all those blocks together to get an overall transfer function. And once you've got a complete model for your system and you've tested it, and it's the output of your model pretty well simulates the output that the real system gives when you give it an impulse or a step input or a series of sinusoids, then you're not done. You then use the model. It's not a homework assignment. You're trying to do this for purpose of getting value out of the model. Models are good for all kinds of things. You can predict the output for some known input. You can determine what input gave rise to a measured output. So we do that all the time when we, for instance, try to record the activity of some neuron using a micropipette and a preamplifier. Well, what we're doing is we're making an inference about what's actually happening inside the neuron as seen through the amplifier. And all we can see is the output. So it's helpful for us to model what that amplifier does and then back calculate what the actual events are inside the neuron. And those of you who collect neurophysiologic data, you're doing that all the time. You just don't realize it because you're using the math that's kind of built into your analysis system, most likely. Sometimes you can use a model just to interpret a system's behavior from some new perspective that you just hadn't thought of. And what we talk about today will be a good example of that. Sometimes you use a model to design a controller to change the dynamics of a system. The second car I bought was a VW Passat, and the guy I bought it from had put a chip in it that adjusted what happens when you step on the gas pedal so it would accelerate faster. And all that was about was measuring out the dynamics of the car's acceleration and putting in a precompensator so that for a given amount of pressing down on the pedal, you would get greater pickup on the car, but not crash. And that's an example of designing a controller to change the dynamics of a system. And then finally, you might use your model to reverse engineer a system. And so I'm just gonna slide video here. You might use it to reverse engineer the physiology of a system, and that's what we're going to do today with the brainstem. So why bother with the vestibulo-ocular reflex, the VOR? Well, this is one of the systems that keeps your eyes on target, and these various gaze stabilizing reflexes are really important for maintaining steady vision. Notice how steady your vision is, even when your head is moving. The vestibulo-ocular reflex is most of what's doing that for you. I'll show you an example later. It's a reflex that mostly operates open loop because it has to be really fast. And so whenever you move your head, it tells the muscles around your eyes to pull your eyes over and keep them on target. And because it has to run as an open loop control system most of the time, it makes it easier for us to model. So it's kind of like a steady cam system that keeps your eyes on target. And when it fails, all kinds of bad things happen. You feel wobbly, and every time you move your head, you can't see clearly. Here's an example of what a normal vestibulo-ocular reflex looks like in just a normal person. If you put a sensor on somebody's head, put some sensors that can measure their eye movements, tell them to look at a spot on the wall and just turn his head quickly over to the left like this. And you measure his head angular velocity here in green as a function of time over about 200 milliseconds. And then here in blue and red, measure the eye movement velocity for the left and right eyes with respect to the head. And now I've flipped them to compare. You can see that just as soon as the head starts moving, the eyes start moving to compensate for that motion. And in an ideal world, they would have exactly the same velocity the whole time, so that as your head is moving to the left, your eyes would stay moving toward the right and stay on an Earth fixed target. And in fact, in a normal human, no matter how you turn their head, pretty much that system works, and that guy's going to have clear, steady vision. But this person doesn't. This is a woman who is going to have a cochlear implant, but she'd had meningitis before, and she lost her hearing in both ears. The question was, does she have any balance function left in either of her ears? Because we want to put the cochlear implant in the ear with the worst overall function, the least function at risk. And what you can see here is when we turn her head over to the left, her eyes don't respond at all. Her eyes just go with her nose until she realizes she's off target and she jumps her eyes back onto target, getting there about 150 milliseconds after the head movement started. And that's true no matter which way she moves her head, different directions, although you can see that her left ear was a lot worse than her right ear where she had some function. And we ended up putting the cochlear implant in her left ear. So what that looks like is something like this. This is a classic video from Halmagi and Kurthoy's group. You can see that when you move this man's head very quickly to the side, his eyes aren't quite on target, and then he jumps back. If you can't see it clearly here at full speed, then I'll show it to you in slow motion. And you can see when you turn his head quickly to the left, now he's not looking at the target anymore, and now he looks back. And so every time his head moves quickly, he just can't see clearly. And in this man who's lost his function in both ears, it's a really dramatic problem in all directions. So how disabling is this, given that some of you may never have even heard about this as a problem? You've heard all about blindness and deafness, but we don't even have a single word in English for loss of vestibular sensation. And partly that's because you've got other eye motion systems that can track things. So for instance, even if you didn't have the vestibulo-ocular reflex, then because you're able to just visually follow things that are moving around slowly, like what's on your screen now, you can do okay. As long as your head is moving slowly, the world's going to drift slowly in front of you and you'll keep your eyes on target just fine. But that's going to fail you if you try to go out for a jog, or really just every time your heel hits the ground. Your head shakes a little bit and it looks like this. Whereas if I stop this and you shake your head, you should still be able to see the text clearly. And people who've lost this function, they can't drive safely and they have a hard time navigating around. So why study this system? Well, because there are lots of disorders that cause problems in the vestibular system. Some of them are listed here. I would encourage any or all of you to load up the AVOR app on your iPhone, which is just mostly for fun, but you can load this up. It takes you 10 minutes to load it, and you can play around and see a sort of live demonstration of how the parts of the inner ear work. And I'd be happy to show that during question and answer time later in more detail. I can actually just put my phone on Zoom. So it's an important clinical system, but it's also a nice place to reverse engineer how the nervous system works more generally, and to encode how neurons encode senses and drive reflexes and adapt over time to optimize performance. So here we're talking about this system, not just because it's a clinically important place where disease happens, but because if you're interested in learning about how neurons work and how the brain learns, this is a great place to work. It's way less complicated than a lot of other things you might try to study. For one thing, the eye is just a ball kind of rotating around in a socket. So it's nowhere near as complex as trying to track the motions of your fingers at the end of your wrist, at the end of your elbow, at the end of your shoulder while you're standing up. So many degrees of freedom, it's really hard to get clean data and hard to model it all. There are only 2 muscles that are pulling the eye in each plane. There are a total of 6 per eye pulling them around in the 3 different planes. There's really almost no external load, and the mass of the eye is essentially negligible. So that simplifies the modeling and the analysis. And there are only 3 neurons involved in this reflex. So for the straight through path, it ought to be pretty straightforward. On top of that, we can control the input for this system because we can put somebody in a chair and move them side to side at different velocities if we want. And we can measure their output by measuring the eye movements, which, by the way, we've done for decades with the Robinson coil system, which was designed by David Robinson here in Baltimore at Johns Hopkins, which involves putting a kind of a contact lens on your eye that has a loop of copper wire in it. And then you take that wire out, you connect it to an amplifier, you put the person in a room where you've generated 1, 2, or 3 magnetic fields that are orthogonal to each other, each of which is oscillating at different radio frequency, generating a voltage in the wires of this coil that tell you where the person's looking. And if you put 2 coils on one eye, you can measure that movement in 3 dimensions. So we can control the input, we can measure the output, and in fact, we can even access some of the signals within this system, not in humans, but we can go in animals and record the output of the vestibular nerve or the activity of oculomotor neurons. So it's a great place to learn how the brain works. We also have a pretty good idea of what it's supposed to do. And although I portrayed it as a really simple reflex with just 3 neurons, it's actually more complicated than that because it's a highly adaptive system that's learning all the time when I take my reading glasses off, now the whole world is magnified differently, and my cerebellum, my brainstem have to adjust quickly, or I'll be bumping into the walls as I walk through a doorway. So it's an adaptive system, and we can study how it works. So I hope I've convinced you that it's worth using as a model system to model stuff. Let's give a try. This is especially good if you know nothing about the vestibular system, because I can demonstrate to you that you don't need to know a lot about a system to model it quantitatively. So first, we're going to go back and define what it does. I just told you. Define all the inputs and outputs. Just told you that too. We're going to draw a signal flow diagram. So, all right, well, here's the simplest signal flow diagram we can. The input, I'm going to say, is head angular rotational velocity. I'm choosing velocity because your neurons really have no idea whether you're facing north right now or facing west right now. They can sense movement of your head, but they can't tell which way your nose is pointing right now. The output is I'm going to use I angular velocity because it makes the math easier. And right now our signal flow diagram is just one block. Like, here's the input, there's the output, and we'd like to know what this system does. And I told you about how it behaves, but we're going to have to narrow this, kind of break this apart into more manageable chunks now. So let's break up that system into its components. And to do that, we need to know a little bit about the anatomy and physiology. So a quick review: head rotation is sensed by these hula hoop-like structures called semicircular canals. There's fluid inside of them, just like the water in this cup. When I turn the cup quickly, the fluid doesn't move with the walls of the cup. The walls of the cup move around it. In this case, if you have little cells or a little gelatinous thing called a cupula here that's blocking movement of the fluid with respect to your head, then when you turn your head, it's going to bend that cupula. It's going to deflect the hair cells that are embedded in that cupula, and that's going to be the mechanical signal that your body gets to say that your head is rotating. The sensors are hair cells, and hair cells are special because they have these little stereocilia that when they're bent in one direction, they leak a lot more neurotransmitter to a nearby neuron, and they make the neuron fire more often. And when they're bent the other way, they leak less neurotransmitter and the neuron fires less often. And so now you've got a little sensor that can measure movement of that fluid relative to your head and therefore convert that into neural signals. Here's the wiring diagram. It's been known for probably 100 years. If I turn my head quickly to the left, the fluid in my left horizontal canal pushes on that cupula, bends the hair cells. You see a sudden increase in the firing rate on vestibular primary afferent neurons. And then through just a couple of synapses, you get the appropriate either activation of muscles or inhibition of the other muscle to pull the eyes back over. So when I move my head to the left, my eyes are going to go to the right. And by the way, the other side of the head is doing the same thing, just the inverse of it, because here your head is moving effectively away from this area. And so the cupula is bending in the other direction. The firing rate is dropping instead of increasing, and all the connections are just reciprocal. And what your brain is really doing is taking the difference signal between your left and right horizontal canals, which is a nice trick engineers do when they've got a sensor that's a little bit nonlinear. If you put two of them in anti-parallel and take the difference off of them, you've linearized the output of that system. So that's how it works in the horizontal plane. You live in a three-dimensional world, so actually, if you turn your head around what I'll call the left anterior, right posterior, or the right anterior, left posterior plane, you've got pairs of canals that are hooked up to pairs of muscles for there too, but we're going to focus just on horizontal. And for those of you who are interested, you've got these three semicircular canals in each ear. They're actually hooked up perpendicular to each other, so that each one of them is listening to the single component of head rotation that is aligned with its axis. And you're getting out a sort of a three-dimensional vector representation of head angular velocity as reported by your vestibular nerve all the time. All right, so now knowing that much more about this system, we can break it down. Instead of having just one big block here, we can say that the sensor end of it, there are these semicircular canals. Right here would be where the signals are coming out through the vestibular nerve from the semicircular canals. I threw in here some synaptic and axonal delays because it's going to take time for signals to travel between one cell and another across a synapse or just along a neuron. They don't conduct at infinite velocity. So there's going to be some delay there. There's going to be a bunch of stuff going on in the brainstem, and we don't know what's happening there yet, but we'd like to know more about it. And then there are the muscles that move the eye and the eye itself, which is sort of the load being driven by this system, and we're going to measure this output. All right, so next thing we're going to do is try to measure or guess or derive a transfer function for each block in this system. So let's try that with this first one. You already know a lot about it. I told you that when you turn your head, say to the left, your head angular velocity has increased. I'm going to use this notation because that's what Dr. Robinson uses in his paper. So if h is your head angular position at a given time, and dh/dt is the time derivative of that, which is head angular velocity, he uses the notation of putting a dot over it. So h dot would be the derivative of head position as a function of time, head angular position, which is angular velocity. So we're just going to call that velocity. The output is going to be some firing rate. But we need to do linear systems analysis. We need a linear function. A linear function is one where if you double the input, you get double the output. And so we need to linearize this thing. The trouble is that neurons, as I showed you before, they're kind of firing anyway, even when you're not moving. Let's say they're firing at 90 spikes per second. And when you start moving, they fire faster. When you move in the other direction, they fire slower. Well, to make this a linear function, we're going to linearize the system by saying we're going to define this function r as the change in firing rate around the resting rate. So it's sitting at an r of 0 all the time, and we can go positive or negative if you turn your head left or right. If you do that experiment of rotating, in this case, probably a monkey, and recording the activity of a vestibular neuron while the animal is being spun around in a chair at, say, probably 50 degrees per second here. You can measure, like maybe this is firing at 90 spikes per second. And when you start ramping up the velocity, the firing rate ramps up. And then if you keep on spinning around and around at a constant velocity for a minute or so, you'll see that the firing rate sort of slowly fades down until you slow down. And actually the firing rate dips and comes back up like this. And so we want to take these empiric data and come up with a relationship that describes what's going on. And you might say, well, all right, when I rotated the head 100 degrees per second toward this ear, I got an increase in firing rate of about 40 spikes per second. So mathematically, that's just saying the change in firing rate is about 0.4 times the change in the head velocity, where the constant here has spikes per second per degree per second. And if you keep on rotating, it doesn't stay up forever like this. It fades over time. And you've all seen an exponential decay before. You've seen this sort of function, an e to the minus t over some time constant. And so you can kind of throw that in there and say, well, I'm going to model this as a jump up almost instantaneously, and then a sort of a single exponential decay over time with some time constant that I can measure from data. All right, so the only trouble is that I'll bet you when I put up this little exponential thing, at least one of you thought, oh God, no, I don't want to do that again. I remember that stuff. It was upsetting, and I finished that class. I don't want to deal with math anymore. But trust me, it's really not so bad. And in fact, you make life easier because instead of dealing with differential equations and trying to solve that in the time domain where it's a drag, what we're going to do is we're going to cheat, and we're going to transport ourselves into the Laplace domain, where all of the complicated differential equation stuff becomes just easy algebra that we remember how to do from junior high school. And then we'll get the answer, and then we'll transform back into the time domain. And this is how you do Laplace transform analysis or linear signals analysis. But I found that Laplace transforms, just mentioning it upsets people who aren't already comfortable with it. So bear with me. All you need is a table and a few rules to follow. So you take any signal in time, like some x of t, it's got a Laplace domain representation. I'm going to say it's capital X of S, where for those of you who are interested, S is defined as this complex variable, which is a number plus square root of -1 times 2 pi times a frequency. If you differentiate that in time, then you just you multiply an S in front of this function. If you integrate something over time, like you go from velocity to position, then you just put a 1 over S in front of it. So you can see already we've taken differentiation and integration and turned them into just simple algebraic changes. This whole transformation is linear. So if you take the sum of two scaled copies of two inputs, you just get the sum of the two scaled versions of their Laplace transform. And then there's some other rules, like if you delay it by some amount of time, you throw an exponential here, multiply by the function. And then there's some sort of classic, you use them all the time, Laplace transforms that you want to know, like an exponential decay with this time constant has a Laplace transform that is really simple. It's just 1 over S plus A, or some people write it this way, where this time constant is 1 over A. I have that there because we're going to use it a couple of times pretty soon. Very specially, if you have an impulse, which is just an infinitesimally short but really high spike of input and drops right back down to 0, the Laplace transform of that is 1. And if you convolve two functions, which I'll explain in a little while, then the Laplace transform of that is the product of their Laplace transform. So this is pretty much all you need to know to be able to use this technique. And yes, there are more details about it, but that's most of it. So for instance, if you put in some input and you measure some output, X1 and Y1, and then you do that again with some other input, and you measure some other output, if it's a linear system, then you know everything there is to know about the system, because from that experiment, you can derive what the linear system's impulse response is. And then you can take any input you want and convolve it by the impulse response of the system and get out the output for any arbitrary input. What do I mean when I say convolution? It's convoluted, unsurprisingly, but the basic idea is that if I, let me annotate for a second. I just need some blank space to work with here and here. Yeah, okay. So I'm going to just draw up here for a second. If I put in as my input a little spike in time, right at time equals 0, and if I get out as my output something that goes like this, say, then this is the impulse response for this system. If instead then I had some new input I wanted to put in that looks like, say, this sinusoid or something in time, I could draw that and say, I'm just going to break it up as a series of an infinite number of little impulses over time. And every single one of them is going to have an output that does something time shifted and scaled. And then I'm just going to get all of those and add them all up. And from that, I'm going to get the overall output of my system. That's what convolution is. And lucky for you, you don't need to do it, because if you're in the Laplace domain, you never have to convolve anything. You're just going to multiply the transfer function that describes this system by the Laplace transform for the input. You're going to get a Laplace transform for the output, and then you're going to go look up in a table what time domain function that corresponds to. You're not even going to have to do that so much today. But I did put in here at this point in the slides more detail on how to plot what's called a Bode diagram. It's a frequency response, which you don't need to know right now. It's just there for your future reference. Important for you, though, is if you have some series of systems where the output of one is the input of the next one and so forth, then those guys, you can just multiply them together to get the behavior of the overall system. And if you have some parallel tree of systems where a common input is delivered to both of these subsystems, and then their outputs are added together, then you can combine them as a single system that is just the sum of those two transfer functions. And that's going to be important for us in a little while. All right, so back to our data. We made these measurements. We got an estimate. I'm not sure why 6 seems kind of short, but if we had a data set with a time constant of decay here that was about 6 seconds, which probably isn't this data set because this looks more like it's a time constant of about 30. We could plug that number in here, and we have 40 spikes per second per 100 degrees per second, and we can plug that number in there. And then we can go back to our table and say, if we look for some function of that form here, it turns out that we can just pull this out of the table and, I have it here. We can pull this out of this table, and now we've got our transfer function defined for the first block in our system. And don't worry too much about the details, but the basic idea is that now we've got a mathematical representation for how the semicircular canal takes head angular velocity and turns it into a change in firing rate on a given prototypical neuron. And we've got a time representation that describes how that works for any random head velocity input that we give in. And there are all kinds of tools like in MATLAB where we can plug that in and plot out how it behaves as a function of frequency, for instance. And I did that with this in MATLAB. What I saw was that this is a system that just passes that signal straight through for higher frequency movements, where in this case, higher frequency is like 1 hertz and above, maybe 10 hertz movements, about like this. As you get down to lower frequencies, it doesn't do very well. And that's not surprising, because I told you before that this is a sensor of head angular velocity. And if you're turning your head at a really, really low frequency, it's just not designed to keep track of whether your nose is pointing north or east right now. But we've already accomplished now one block of our system is modeled. Let's race through and do a couple of others. And usually the easy blocks to model are the ones that are near the input or near the output. So let's model those. And then I'm also going to model these delays, because the delays, again, you can just pull out of the table and say, well, I measured, this is in a guy, patient of mine. I used the Robinson coil system. I turned his head real quickly. I measured his eye movement response. Here you can see his eye movement in red almost exactly followed his head movement. But there was a little bit of a time delay. It was about 5 to 7 milliseconds here. And so that tells me that there are just some finite transmission speed issues of signals going across synapses or along axons. And we can say that this overall system has about 5 to 7 milliseconds of delay. We can go back into our table and say, well, okay, here's a time function where there's some amount of delay, and its Laplace transform looks like this. So I'm going to just make that my block. I can plot that in MATLAB. It's got no gain and it's got no phase lag until you get out to higher frequencies. And now I've got another one of my blocks in my system model. So let's go do one more. It's going to be really similar. In this case, we're modeling movement of the eye angular velocity, as the output for a system whose input is firing on an oculomotor neuron. And same thing, you can go in with a microelectrode and record from the activity of oculomotor neurons that are going to those muscles I showed you. And you can say, well, how does the firing rate, I can't really change the firing rate of it, but I can just measure the firing rate while the eyes are moving around a lot during experiments. And then I can come up with a rule that says, well, the firing rate that I recorded at any given time seemed to have 3 components to it. One was just a baseline firing rate, like it was firing anyway at whatever, 40 spikes per second and varying around that. But then also there is some amount of firing that seemed dependent just on the current eye position. So if the eye was looking 10 degrees or 20 degrees off to the side, then the neuron would be firing, say, 10 spikes per second more or 20 spikes per second more. And if the eye was looking to the other side, same thing. It would be firing by 10 or 20 spikes per second less than its baseline. And this A here is just a whatever constant describes the gain of that. But then also it turns out that if the eye is looking, from left to right to left to right, while it's crossing the midline, the firing rate also depends on the velocity with which the eye is moving. So if the eye is moving really fast, then the firing might be faster. And if the eye is moving really slowly, then it fires slower. And so I'm going to say that the firing rate also depends on the eye velocity with some scaling factor B here. I'm going to do that same trick we did before to linearize this system. And I'm going to define this change in firing rate as the momentary firing rate minus the baseline rate. And now this is a linear function. Again, because if I doubled E, for instance, if I double one of these guys, I need the output to be doubled also. And it doesn't work if you've got this constant that's sitting here. So you just linearize by subtracting out the baseline. And now you go and look in your table that I showed you before and see if you can find Laplace transforms that represent this function. Remember, I told you if you differentiate in time, you just throw an S in front of the transform. So you can sort of see where this is going. That equation I just showed you could be rewritten as something like this, where it's a constant times 1 over S times the time derivative of E, so it's I velocity, plus a constant times I velocity. You can gather these things together. Here we're doing basic algebra, not scary differential equations. You can rearrange this all and come up with a transfer function that describes the behavior of the oculomotor muscles moving the eye. And it's kind of similar to the type of functional form that we saw before. Over these frequencies, it looks like it's sort of a high pass filter, kind of surprising, but it is. And we can measure out the parameters for it from an actual experiment and get values for these numbers and stick them in there. And now we've got, it looks like almost the whole system is worked out. The only trouble is that we left the hardest part for last. So I'm going to kind of race through it because you don't need to know all the details, and you can read the Robinson paper if you want. But here we can't really control the input, and we can't even really measure the output exactly. And this is the part that we want to know about. So what do we do? Well, one thing we can do is we can go back and measure the whole system and its behavior and model it. So again, we're going to move the person around side to side. We're going to measure his eye movements side to side. And we're going to treat this whole thing as one big block. And we can do that experiment by spinning somebody around in a chair, measuring their eye movement responses. Here, just as soon as the chair starts rotating 50 degrees per second, the eyes are going 50 degrees per second in the other direction. They can't turn forever, so they beat back now and then. But that velocity fades to nothing within about a minute until you stop the chair, and then your eyes will go in the other direction. You can measure an initial gain, and you can measure a time constant from this. And you can come up with an overall transfer function for the entire vestibulo-ocular reflex. It's just the same as what we saw before, but with different parameters from your experiment that you measured. So now what do? I told you before that you could take a system like this with a bunch of subsystems, and if they're in series, you could just multiply them together to get the overall system. And I'm telling you that the overall system has this behavior. So maybe what we could do is we could take this transfer function and then divide out these 3 other blocks and get some estimate for what's going on in the brain. And that's what David Robinson is doing. So there are a couple of things just empirically. What we can see is that whatever the brainstem is doing, it's changing the behavior of the system from what the semicircular canals were doing to what the overall VOR doing. And it's a little underwhelming, to be honest. All that it seems to do is that your brainstem is making the system work better at lower frequencies. Who cares? Like 0.01 hertz is super low frequency. Why would you even care? Well, part of the reason is that, remember I told you before, you've got other ocular following mechanisms that can follow movement, but they don't do well at high frequencies. So they're doing great. They're doing great at low frequencies, but they fall off as you get to high frequencies. And so part of what your brainstem is doing is making sure that you don't have some gap region where neither your vestibulo-ocular reflex nor your oculomotor following smooth pursuit reflexes, where neither one of them is working. And what the brainstem is doing is pushing the function of your vestibular system down to cover up the region where your other oculomotor systems start to fail. So that's worthwhile. That probably saved somebody from getting eaten by a tiger once, and they went on to have children, and their great-great-great-great-great-grandchildren became your ancestors. Right, so now what we do is we're going to combine all these blocks to get an overall function, and then we're going to use this, and we're going to try to reverse engineer what the brain is doing. So we're going to take, here's the overall transfer function. We're going to divide out these sub blocks, and we're going to come up with an estimate for what the brainstem neural signal processing transfer function is. And this looks a little hairy, but if you simplify it some and you ignore the delays here because they're not that important for this purpose, you can see a few things about what's going on here. One is that it seems like the system took the time constant of the semicircular canals and swapped it out for this longer time constant of the VOR. That's what I was just telling you, that's working at lower frequencies, longer drawn out signal. And then it also seems like to make the math work, there has to be a 1/s somewhere. And I told you before, that's a Laplace transform for integration of a signal in time. So, well, oh, and there's a -1 because after all, when your head goes to the left, your eyes have to go to the right. There's this thing that kind of stretches out the time constant of the system and makes it so the VOR responds for longer than the semicircular canals alone would do. There's an integration from velocity to position, and that's because your eye control system needs to have neurons firing to hold your eyes off to the side. If you try to just look off to the side for a really long time, then without this system in place, your eyes would always just retract back to the middle. And you need this, what's called a neural integrator to do that behavior. And then there's this other element that helps to effectively make up for the fact that the eye does have some mass, and your brainstem is making it so that it compensates for the inertia of the eye. So a best guess for what the overall brainstem is doing would be mapped out like this. It inverts, it has some gain, it stretches the time constant, and it's got this funny network inside that includes a 1/s. There must be some body of neurons that takes in a signal in time and adds them up over time. It integrates them over time. And before Robinson and his colleagues did this model, nobody had ever really, I guess, quantitatively thought to go and look for some neurons that do that, that integrate signals over time, not just over other inputs. And believe it or not, it exists. So knowing all that they knew, now they had a hypothesis to test. And one of the beautiful things about this work is that, you know, the brain is full of a trillion neurons, and it's hard to know what to do where. But if you've got a solid testable hypothesis, in this case in the form of a quantitative model, well, now you can go and test that hypothesis. And even if it's wrong, at least you learned something solid. And sure enough, Ed Keller, who, fun fact, was on the faculty of the Department of Biomedical Engineering at Berkeley, where I was a graduate student. He was one of my professors. He was a postdoc, I guess, with David Robinson. And went off and found this, recorded from these neurons in an area called the nucleus propositus. It's a group of cells in the brainstem. They're right next to the cells that run the eye muscles. And sure enough, these cells, they take a velocity input, they create a position output. And this has real import in clinical medicine also, because you can get a stroke in that area. And if you have a stroke in that area, or if you make an experimental lesion in an animal, then the subject, the patient, gets gaze paretic nystagmus, which is that problem I told you about before. If you ask them to look off to the side, they just can't keep their eyes over there. Their eyes keep on drifting toward center, and then they look back because they know they're supposed to look there. And so their eyes are always drifting out like this all the time, no matter which way they're looking, to the left or the right. Their eyes can't stay out that way. And that is gaze paretic nystagmus. It's sort of the signature finding in people with a stroke in this region. And what about these other signal processing blocks? This one that kind of stretches out the time constant, it's called velocity storage, I think, in the paper. And as far as I know, there isn't a precise group of cells that does that, but the nodulus area of the cerebellum seems to have a key role in it, because if you lesion that or you have a stroke there, then people lose that ability. So to bring this all back, why should we model anything in biomedical engineering? Well, everything that happens by definition is a signal in time. And biomedical systems are full of dynamic control systems. They're actually super complicated most of the time. They're highly nonlinear and they change over time, but you can usually do a pretty good job of modeling a nonlinear differential equation-based system with just simple linear system stuff. You can get a pretty good approximation. You can get a long way, like Dr. Robinson did in this review paper. Purely computational models, often they provide little insight, but if you use a linear systems model coupled with generating hypotheses from the model that you then test by making empiric data acquisition experiments, you can make a lot of headway. I mentioned before that these differential equations are kind of painful. It's upsetting. You forget it as soon as you finish the final exam in the class. But switching over into Laplace domain makes your life easy, and it's a technique that you should learn about if you haven't heard about it. The other nice thing is that the math is the same. Linear systems is the system used for modeling electric circuits, for chemical engineering, heating, transfer function thing, for measuring the behavior of economic systems. If you learn linear systems modeling, you can leverage Simulink or MATLAB or SPICE, all these computational tools to model a very complicated system that may go across multiple physical realms, like, for instance, movement of molecules of air, moving the eardrum, moving the middle ear bones in a mechanical linkage series, moving the fluid in the inner ear, moving hair cells, changing neurotransmitter release. You can model the entire inner ear for hearing using these same techniques. Why should you model anything? Well, you can draw inferences about internal structures and mechanism. You can point toward new hypotheses and experiments. You can formalize and quantify what you already know about a system. And you can use it as a shorthand to describe a system. If you tell me, oh yeah, that system, it's a high-pass filter with a critical frequency of about 100 hertz, I know a lot about that system with just a few words, because the model is effectively parameterizing a complicated thing into a couple of parameters. You can use this model to predict the behavior for novel inputs, like I mentioned before, or estimate the input for some known output. Most commonly, the output is a thing that you can actually measure, like the sound that comes out of like the sound signal that comes out of a microphone is telling you what the microphone's input is. Sometimes you just make pretty pictures, honestly, when you model something. Experiments are hard. Getting real empiric data is hard. But you can use a model to effectively interpolate in the sparse real data. You can fill in as though you did 1,000 experiments by creating a model that you vet with your empiric data. Effectively, that's what's done if you're designing a jet airplane. You don't want to crash 1,000 airplanes to test, different ideas. Or if you're designing a nuclear bomb, I mean, you don't want to be blowing those up every weekend. So instead, you create a model that can get you the answers that you want and let you run virtual experiments rather than doing very costly or dangerous experiments. You can test ideas way more efficiently, as I just mentioned, in a model than you can by getting empiric data. So you really want to use the model to formalize your hypothesis so that you maximize the value of the very difficult experiments that you're going to do to get empiric data in animals or with people. And if nothing else fails, you can improve your dating app profile by ambiguously mentioning that you model, professionally. I think that's all I've got, but I'll just end by mentioning that I was one of the last people, I think, who had the benefit of hearing David Robinson himself teach this material using his handwritten lecture notes. Here, I can't really put these online, I guess, but for any of you, Hopkins, I'm sure that we can share it. I would highly recommend reading through Dr. Robinson's own notes. This is how he presented this material, and it's startlingly clear. And so I'd strongly recommend it to any of you. And with that, I'll stop.